Start. Okay. So we are ready to go. We can put a little red light outside the classroom, on air, red light turns on. All right, so today's focus is going to be, well, first of all, the ungraded assignment. If you have a chance to work on it, great. If you do not, it's okay too. So we'll talk about that today, basically as a warm-up, because we have been talking about subroutines on Wednesday after the exam. So what we'll do today is to kind of continue with that topic. And this is a particular program. Instead of saying, before this, do something and do something over here and continue to do something, this one is a lot more specific, don't you think? We got, x equals to 0 or x gets 0 on line 8. And then we got line 2 saying x gets x plus 1. But those are the only two lines that you recognize from before, okay, the assignment statements. Everything else are about subroutines. So that makes this program kind of, interesting in that way. But I named the subroutines in a very boring way. One says add 1 because it adds 1 to x. The other one says add 2 because effectively it adds 2 to the variable x. But it's not doing it using the obvious way of x gets x plus 2, but instead it's calling add 1 twice or invoking add 1 twice. Yes?
Do we not worry about the parameters being passed in this class?
Not yet. So we'll get to that. We'll get to all the good stuff like parameters, local variables, and maybe even records or structures close to the end of this semester. All right. So let me go ahead and copy this code into a spreadsheet because this is like showing in the middle of the whole screen and I can't really move it around very easily. So I'm just gonna, this is a good one to use. Come on. There we go. The font doesn't look very good, but can't seem to resize it by double clicking it, but I can always do it this way. And then each row is having a kind of odd size too, so I'm gonna fix that. All right, that's good enough. All right, so we have the code showing on one page. And let me see if I can. Yep, there you go. So it worked this time, didn't work the other time. And then we'll use the other sheet as our trace. So one side stays on the pseudocode, the other side displays the trace. All right. All right, so finally we got everything all set up using one sheet as the trace. Now with this sheet, we always need line number as a column. Okay, that one is not inevitable. You always need that. But in this case, there's no comments because there are no conditions to evaluate. There are no if, there are no while, there's no repeat until. So we don't really need comments as a column. We do need one column for the local, not local, but we need one column for the variable x. So x takes a column, and that's it. So to start with, we just need A and B as columns. B as a column is going to start with an unknown value because we don't really need to know what x has because we're going to change it right away. And then the pre is it's basically indicating that variable x starts with an unknown value. So this is the beginning of the entire program. So now the first question is, with subroutines, where do we start? Because line 1 up to line 3 is the definition of the subroutine add 1. Line 4 to line 7 is the definition of the subroutine add 2. So the first line of code that is outside of any subroutine definition is line 8. So we start execution from line 8, okay? Not line 1 anymore. Okay, so here's line 8. And line 8 says x is initialized to 0, so we just put a 0 into the column x. Then we move on to line 2. Just kind of excuse me, the next line. This is line 8. I said one thing, I wrote something else. This is line 8, and we move on to line 9. Okay, so line 9 is something that we have seen already. On this Wednesday, we talked about how to do the invocation of a subroutine, and we're going to do exactly the same thing, okay, today. So there are two things you need to do. The first thing is you have to allocate the leftmost available column and label it the return line number, okay? So you look at the entire spreadsheet, column A is used, column B is used, so the leftmost available column is going to be column C. So we look at column C and go like, well, you're it, okay? Because you're the first unused column from the left-hand side. So we label this return line number, and then we use it right away to help us remember when we are at the end of whatever subroutine we are calling or invoking, we have to get back to the line right after the invocation. The invocation is on line 9, which means when we come back, we have to come back to line 10, the line that is after the invoke. So then we write down a 10 here. Okay, so we can make columns a little bit narrower. There we go. So that's the first thing you need to do when you're invoking a subroutine, is to remember where are we supposed to go back to when the subroutine is done. Now that we have done that, then the next thing we do is to continue execution in the subroutine itself. So in this case, because the invocation calls add1, so we continue execution in add1, which is line 2, because line 1 is nothing more than a marker that marks the beginning of that particular subroutine. Line 2 is really the first line that actually has something to do. So when we get into a subroutine, we start execution on the line below the defined sub line. Line 2 doesn't do a whole lot of crazy stuff. Okay, all it does is to add 1 to x. X goes from 0 to 1. Then we get to line 3. Line 3 doesn't seem like it has something to do, but it actually has quite a few things to do. Once again, there are two things to do. The first thing it has to do is to find the leftmost, so it has to find the rightmost, okay? I take it back. It has to find the rightmost column that is labeled return line number. In this case, it's like, at this point, it doesn't sound like, okay, what do you mean by the rightmost? There's only one column labeled return line number, okay? But keep that in mind, okay? We have to use the rightmost return line number column that is still labeled as return line number. So in this case, okay, it's column C. What does it say? It says we have to go back to line 10. So you basically write down line 10 here to remind you that that's where you need to go back to. And then there's the second thing you have to do. The second thing you have to do is to deallocate column C. So the way we can remember the column C is now deallocated is really just to copy and paste return line number, and then we use a strike out font to strike through, okay? So that now it is indicating that this column C, is once again available. Is that okay so far? Do we have any questions about the calling or the invoking of subroutine add1 and how we got back to where we left off before the invocation? Is that okay? All right. Okay, so now we are on line 10. You look at line 10. Line 10 says, let's invoke the subroutine called add2. Well, it's the same thing, okay? Remember where you're supposed to come back to using a column. But which column should we use? It's going to be the leftmost available column. Column A is still in use. Column B is still in use. Column C is not in use anymore because we explicitly deallocated it. We marked that that column is now available. So now we're going to reuse column C and go like, oh, okay, let's go ahead and remember the return line number of another invocation. So this time the invocation of add2 says we have to go back to the line after the invocation. Technically, there's no line 11, but we do have a post, don't we? So that's what we put down here. We just say post, okay? So when we come back, everything is done. That's basically what we are saying. So we still leave behind a piece of breadcrumb, okay, just so that when the subroutine is done, when this invocation is done, we know where to get back to. All right, now that we have left behind a breadcrumb, it's time to get into the subroutine. This time I'm invoking add to, so to continue execution, I go to line 5, which is the line after define sub add to. So we go to line 5 here. Do we have any questions before we continue at this point? The mechanism is still the same, even though we're invoking a different subroutine. The tricky part, or the part that you really kind of have to remember, is we are deallocating column C and then we reuse it again. Is that okay? All right. So on line 5, line 5 itself is not a problem. Okay, line 5 says add 1. Okay, we're invoking add 1 here. What do? We have, we have to remember. Okay, we have to. But which column should I use for that purpose? What is the leftmost available column at this point? Column D, very good. So now we are using column D and say, well, since column C is right now in use, we have to use column D. So column D is another column that is now labeled return line number. And where should I go back to? Which line? Line 6, exactly, because the invocation is on line 5. So we go back to line 6, and then we are ready to go. And where do we go next? What should I put here as the line number? Go back to line 2, very good. So go back to line 2, and the effect of line 2 is fairly easy to do because line 2 is just x gets x plus 1. So it is at this point that x is incrementing from 1 to 2. Okay, that part is easy. Then we go to line 3 again. Line 3 is a return, is an n defined sub. So at the n defined sub, what do we do? Well, okay, very good. Okay, so we have 2 return line number this time, okay? Because at this point, both column C and column D are labeled return line number. So which one do we use to return? It is the rightmost column that is labeled return line number, which is also the most recently one, okay? The most recently added return line number column, it means exactly the same thing. But on the spreadsheet, we just say the rightmost, okay? The rightmost column that is still labeled return line number. In this case, it is column D. So column D says, let's go back to line 6. So, okay, so this says it go back to line 6. So that's where the next line is. Okay, so this is still line 3, and then the next line is going to be line 6. But at the same time, we have to remember that column is not of no use to us anymore. We have just used it. So that means it is now deallocated. So column D is now deallocated. If we need another column, we can use it back. So now we go to line 6. What does line 6 do? Invoke add 1 again, okay? So what do? We allocate the leftmost available column. Which column would that be? Column D again, because it was just deallocated. So now it is available again. So we reallocate that column for return line number. And then we say, well, it's useful to remember where to get back to. The invocation is on line 6. So where do we go back to? 7. We go back to line 7. Very good. So the return line number is 7. And now we can continue on with the subroutine that is being invoked, which is add 1 starting on line 2. So we put line 2 over here. Line 2 is adding 1 to x. X goes from 2 to 3. Then we hit line 3 again. When we get to line 3, which is the end of a subroutine, it doesn't depend on which subroutine we are ending. Every single time we get to end define sub, this is what we do. Okay? We find the rightmost column that says return line number. In this case, it's column D again. It says we have to continue execution on line 7. And that's where we're going to go. Okay, so we put 7 over here. And then we also have to remember that this column is not useful anymore. And then we deallocate it. Now we continue execution on line 7. Line 7 says, end define sub again. What do? Exactly the same thing that we did. Okay, we locate the rightmost column that is labeled return line number. Column D is not labeled anymore. It just got deallocated. So the rightmost return line number column is now column C. Column C says continue execution at post. That's okay. Just write down post right after 7. And then we still have to remember to deallocate it. So that means on line 7, we have to mark column C as deallocated. And after that, we continue execution at post, which means, oh, we're all done. There's nothing else to do. Yep. Hmm? What do you think? Because I've been talking about that the whole time. It bored me already. Okay. Aha. Okay. So for the rest of the class, what did I say about red line? What does it represent? Return line number. That's it. So red line is return line number because otherwise I have to type a lot more. The column gets wider unnecessarily, and that's why it's just called return line number or red line pound. Is that okay? Are there any questions about this trace? Because if there are any questions about this trace, it is probably a good idea to address that now instead of later, because the next thing we're going to do is what I promised, recursion. We don't need parameters. We don't need other things to talk about recursion. This is what we need to talk about recursion. That's all. Are we ready? Mm-hmm. All right. Okay. So I'll keep this around, okay? I'll use exactly the same spreadsheet, but this time we'll talk about recursion. Okay, so here we go. This is a recursive subroutine. Define sub, and we'll call this, sub 1, okay? Subroutine 1. And inside it has a conditional statement. I have to make sure that this is not a homework assignment, so I have to be extra careful about this. Okay, so I know what to do. So we'll say if x is greater than 0, then we perform the following operation. We say x gets the floor of x divided by, I don't know, let's say 3, okay? There we go. And then we invoke sub 1 again from here. And then the else is just nothing to do, okay? So if there's nothing else to do here, we just say and if. And then we say and define sub. So outside of the subroutine, we're going to initialize x to something. So I want to initialize x to a value where it has to go through the subroutine at least twice or 3 times. So that will make it, 28. 28 will go through like 3 times. Yep, so let's go for 28. And it also shows you the use of the floor function, right? So that's good. So x is 28, and then we invoke sub 1 here, and that's it. So it really helps to use indentation so that we know what is inside what else. Okay, so we're going to do the indentation. And then one more time here, because both of these lines are inside a particular invocation, inside the conditional statement. There we go. All right, so there we go. So we got the subroutine, and now it's time to look at the trace. And I can reuse this window because this was displaying the algorithm. We'll use it again to display the algorithm, and then use sheet 6 to display the trace of this particular algorithm. So technically speaking, this is recursion. What recursion really is a subroutine invoking or calling itself. And we have that, okay? We have subroutine sub 1 invoking itself. So it is recursion. It has no use of parameters or local variables. Both of those concepts we'll talk about later, possibly today. But it is recursion, very simple, doesn't do a whole lot of crazy stuff, but we'll check it out. We'll find out what it does. So we start with the columns. So we have line number. This time we do need comments because we do have a conditional statement on line 2. So comments is needed. We have one variable x, so that's the only variable that we'll be tracking, which is x. And I typically want those columns to be in this particular order. Okay, precondition, once again, x doesn't have to have a particular value because the first thing we do is to override it. And then next, we'll start the program on line 7, because line 7 is the first line that is outside of the definition of a subroutine. And all that does is to initialize 28, x to the value 28. Then on line 8, we have an invocation. We already know what an invocation of a subroutine is supposed to do. We have to allocate the leftmost available column, which is column D in this case, label it return line number. And then we have to remember, where are we supposed to get back to when the subroutine is done? This post, exactly, because there are no more lines after line 8, which means when we come back from the subroutine, it is done. And then we continue execution in the subroutine that we are invoking, which is sub1, starting on line 2. And line 2 starts with a conditional statement, so we have to answer the question, is x greater than 0? Yep, okay, it is true. So we go to the then portion of the conditional statement, which starts on line 3. Line 3 changes x by updating it with the floor of x divided by 3. So 28 divided by 3 is 9 point something. The floor of 9 point something is just 9. So x gets 9. Then we go to line 4. Line 4 is an invocation of a subroutine. So now what do? We are inside the subroutine that we are supposed to be invoking. Is that okay? Do we have to do anything special? I mean, what is the magic of recursion? Exactly. In other words, I have to quote Poe's father in Kung Fu Panda. Okay? The scene that you want to put in front of you right now is when he's a duck, right, or goose? Yeah, exactly. The goose, right? Okay. So he told Poe, the secret ingredient of the soup is nothing. There's nothing special about this invocation. What you have been doing all along, that's the same noodle, the same soup. Okay? There's nothing special here. Okay? Now I can already see most people walk out of this class remembering Kung Fu Panda, but not a single thing about recursion. That's the power of movies, right? Okay, so nothing special. What do? We allocate the leftmost available column to remember where to get back to. Right now, column E is the leftmost available column. Label it return line number, okay? And what line am I supposed to get back to? This one gets a little bit tricky, but not that tricky. It has nothing to do with recursion because the invocation is on line 4, but we don't really track line 5. So when we get back, we get to line 6, okay? So the return line number is line 6 in this case. But other than that, nothing special. But where are we supposed to go then? Because we're in the subroutine that we're invoking. We're already in the middle. So when we're invoking this subroutine, where do we go? Just like any other subroutine from the beginning. There's no secret ingredient. Same old noodle, okay? So we go back to line 2. That's it. Okay, so maybe the magic stuff is when we're returning. We'll check that out. So we ask the same question again. X is greater than 0 is true because it is 9. And then we go to line 3. We update x again. X becomes 9 divided by 3, which is 3 exactly. So the floor of 3 is 3 itself. We store that here. We go to line 4. What are we going to do? Well, since we did it last time already, we allocate the leftmost available column, which is F this time. Label it as return line number, and then we mark down line 6 is where we go back to because we have been here already, okay? So we kind of know what to do. And then we continue execution at the very beginning of the subroutine, which is line 2 again, which asks the same question. X is greater than 0 is true. Then we go to line 3. X becomes 1 because 3 divided by 3 is 1 and the floor of 1 is 1. Then we go to line 4 and go like, oh, come on, give me a break. Same stuff again. Okay. And then we get back to line 2. We are not done yet. X is still greater than 0 because x is 1. So we go to line 3, and then this time x is finally 0 because 1 divided by 3 is 1/3, and the floor of 1/3 is 0. Okay. Then we go to line 4. Really? Yes, one more time. The idea is to totally demystify the term recursion. It's like, no, it's not that mysterious. All right. So this time when we get back to line 2, finally, okay, finally the answer is x is already 0, so x is greater than 0 is false. Oh, finally, we don't have to do all that stuff again. So now we go to line 6 right away because the condition of the conditional statement is false. So we don't have anything else to do. We stop the recursion. So on line 6, what do we do? This is recursive subroutine. So there's got to be something magical about the returning from a subroutine at the end of that subroutine. Nope, same old trick. Okay? So if invoking a subroutine is the same noodle, returning from a subroutine is the same soup. There's really no magic about this. This has been the same noodle that you have been eating, since the beginning. Okay, so on line 6, we do exactly the same thing. We locate the return line number that is the rightmost, okay? We got a whole bunch of return line numbers, but only one of them is the rightmost one. So it's not D, it's not E, it's not F, it's not G, it is H, okay? So H is the one that we need to use, and guess where it tells us to go back to? Line 6. Okay, fine. We'll get back to line 6. And then we have to remember to deallocate this column. So we copy and paste the label of the column, and then we just say we use a strike through to mark that it is now not useful anymore. So now we continue execution on line 6. What does it say? And define sub. What do we do when we're at the end of a subroutine? We locate the rightmost return line number column, which is not column H anymore, it is gone, column G, and then we say, what does it tell me to go back to? Line 6. Okay. So we go back to line 6 again, and now that column G is no longer useful, mark it as such. Now we execute line 6. What do we do on line 6? Locate the rightmost return line number column, find out where it tells me to go back to. Line 6 again. Okay. Go back to here. And then we say that column is no longer of use to us. Deallocate it. Now we execute, guess what? Line 6 again. What do? Find the rightmost return line number column, which is column E this time, and let it tell us where we're supposed to go back to. Line 6 again. And then that column is of no use to me, so we deallocate it. And then finally, this time when we execute line 6, let's check out where we're supposed to go back to. Oh, the rightmost return line number is now column D. Finally, it tells us something that's different. Let's go back to post. So post is here, and column D is not of use to us anymore. We deallocate it. Now we continue execution at post, which means we're done. Okay, nothing else to do. That is recursion. How was it? Exactly. It's the same soup and the same noodle you have been eating. Huh? That's good. That means you understand recursion. Yep. Okay. Well, it's just that the term recursion, it's recurring, but the mechanism is not. Okay. If you do not take this class, so let's say you take this class from somebody else, okay, who does not use a trace like this to show you the mechanism of invoking a subroutine and returning from a subroutine, you won't actually see this mechanism until Crisp 310. And a lot of people push Crisp 310 to the last semester. So that means by the time they take Crisp 400 and also 430, both will talk about recursive subroutines. They would not actually have an understanding of the mechanism behind it. They can see the effect of it, but they don't understand how it works. And I think it is important to understand how it works. Yep.
I don't think I completely understood how you got the return line post in the beginning.
Okay, so you're referring to, okay, so when we execute line 8, okay, so this is the row, and this is the other thing that's really good about the trace is you can go back in time to any slice of time and say, okay, right at that moment, what happened? And we can go back and re-explain that. So on line 8, it is invoking sub 1. And there are two things, hold on a second. There are two things that we have to do when we invoke a subroutine. The first thing is we have to remember where to get back to from the perspective of the invoked subroutine. So from the invoked subroutine's perspective, we don't want to go back to line 8 because we'll just be invoking the same subroutine again. So we have to go back to a place that to continue execution. But there's nothing after line 8. So the only thing we can say is post. We just kind of imagine that there's a line ending the entire program called post.
Okay.
So go ahead. Is that it? Okay. You go ahead.
Why do you start on line 8?
Why do I what?
Did you start on line 8?
I did not start on line 8. I started on line 7. Are you referring to the trace or are you referring to the algorithm? This is the algorithm, this is the trace. So which sheet are we referring to? Okay. Yep.
So you started with line 7 because it was the first line of executable code because the subroutine was defined between lines 1 through 6.
Correct. Yep.
And then it went to 8, and then the next line after 8 was post, and that's where you got the return line.
Yep. Exactly. But you don't get to post until you're done with the invocation of the subroutine, right? So this is a very interesting example because we only got one subroutine, right? We only have subroutine sub 1 defined exactly once in this particular program. But we have, yeah, go ahead.
So is recursion just another kind of a loop or a loop within a loop?
Well, I'm glad you mentioned that because it is a form of repetition, but it is not the same thing as a loop. Okay? So keep that in mind because that was a very good question. It's a very good observation that we are doing the same thing over and over again. So you look at line 3 and 4, we did those, what, how many times? Like, you can count. 1, 2, 3, 4. So we do those lines like 4 times, which is kind of like a loop, okay, doing something 4 times, but it's not exactly a loop. So it can have the effect or the appearance of a loop, but it can do more than a loop. What can it do more? You can deal with recursive definitions. And you go like, recursion and then recursive definition. So today is all about recurring stuff, right? So what is a recursive definition? You have seen recursive definitions already. It is basically a structure that has substructures that look like the structure itself. We also call those self-similar structures. So you take a big piece, you look at the smaller pieces or the components. Each component look kind of like the big piece, except they're each smaller. So do we see anything like that on a daily basis?
Yes.
Okay, and what would that be?
Calendar year.
I wouldn't say calendar year. Yep.
What are those Russian dolls that have like smaller dolls inside?
That would be one. Yep. That's one example, but that's a very simplistic example, where recursion is not needed to solve that problem. But nonetheless, it's a very visual example. So for those of you who don't know what I'm talking about, okay, are they really just called Russian dolls?
No, I can remember.
Okay, I'm pretty sure they have a very specific name. Okay, Matryoshka doll. Okay. There you go. All right, so it is a one form of recursion, okay? So, ooh, look at that collection. Just like recursion, some people get obsessed with these things. Look at this one. Okay, but you don't have to be that exotic. When was the last time you used a computer today? Yeah?
I was gonna say, what about like a box set of DVDs? Because then you've got like the box on the outside.
Uh-huh. But the DVD doesn't look like the box itself, so therefore there's no, so the self-similar structure part is not there. What do you think? Yeah,
Would it be like a folder inside a folder?
a folder inside a folder, exactly.
Oh, what's inside a computer that like the mothership switches?
That one is not that self-similar, okay? But the folder within the folder is the concept. So what can the folder contain? Files and other folders, right? What can those other folders contain? Folders and files. What can each one of those folders contain? Folders or files, and so on. Okay, so a folder is a self-similar structure. Okay. That may not be a very direct analogy.
Oh, you could say the Fibonacci sequence?
Fibonacci sequence is one, so we can look at that, okay? Okay, imagine you're a squirrel, okay? Okay. If you're a squirrel, okay, what do you think on a daily basis is actually has a self-similar structure? Okay, imagine you're not a ground squirrel. Ground squirrels are excluded from this discussion. Branches, exactly. So a tree is a self-similar structure, okay? Let's look at the picture of a tree in case you have never seen a tree before. I think in a few hundred years, that might actually happen. People would.
How would it be if there's no trees for oxygen?
Huh?
If there's no trees for oxygen, how would it be?
You just need a power source. I mean, there are other ways to make oxygen, yeah. Or maybe people at that time would not need oxygen anymore. We are assuming organic life form, so there you go. So if you look at the tree, okay, you look at the main trunk of a tree, you imagine you're a squirrel going to a particular leaf on the tree, okay? So you're going up the main trunk, and then at the first place where it's branches off, okay, you have to make a decision, okay? And the moment you branch, you turn to one particular branch, it looks just like the main trunk, except smaller. And then you get to a place where it splits off again, you take a turn, and that smaller branch looks just like the previous branch, except it is smaller. So you keep navigating like that until you find a leaf on the tree. Then you have to stop because a leaf does not split off into branches any further. Is that okay? So if you want to look for a self-similar structure, a tree is a very good example of a self-similar structure. But if you look underground, look at the root system, same way. The root system of a tree is also just as quote-unquote recursive, because if you look at the main tap root, it splits off into smaller roots. You look at each one, it splits off into even smaller one, and then each one splits off into even smaller ones. How small do you think roots can get? Microscopic. That's how they break concrete. They get into the tiny little gaps, okay, of concrete, and then they just keep expanding and expanding, and then concrete cannot even deal with that. So that's a good example. Now, but tree and folders are related. How do you think this is related to folders? They're both recursive, but more so than that, okay? One branch can only come from one particular main branch. It cannot come from two different branches, okay? So a smaller branch can only belong to one bigger branch, and that bigger branch can only belong to one even bigger branch, and so on. Folders are the same way. A folder can only be contained by one other folder, the parent folder. One folder cannot be contained by two different folders. Okay? That's why trees are very interesting structures in computer science. This class is kind of way below that particular level when you can start to see, oh, okay, so trees are really, really important. But as you go on and move on to other computer science classes, you will start to recognize that the tree structure is a very recurring theme in computer science for interesting reasons. You can even look at a program as a tree. Okay, in C, C++, any practical real programming language, they're just like a tree. Okay, you look at a conditional statement. It can contain multiple statements. Each one statement can be a while loop. You look into that while loop, and it can contain multiple statements. One of those statements can be another conditional statement. You look into that conditional statement. The then branch can contain another loop, and so on. So it has that kind of recursive structure again. And once again, it is a tree. Even expressions are trees. Okay, so yes, I'm going off on a tangent on trees now. In case you're wondering, is tech going off on a tangent again? Yes, affirmative.
Quick question.
Yes.
So recursion can be used in, say, file management or database query?
Yes, file management uses it all day long. When you need to, hold on a second. When you need to nuke a folder, what do? Well, lucky you guys, you do not have to use any command line to delete a folder. You just click on the folder, right-click on the folder, say delete, right? Or click on it, select it, and then press the delete key, and it automatically happens, right? But if you need to do it by hand, the rule is if a folder is not empty, you cannot remove a folder. So what do? You go down to the next level. You go like, can we delete that folder? No, it has stuff in it. You go into that folder. It has sub-folders. Can we delete that folder? No, it has got more stuff in it. So you have to get down to a folder where it only contains files. Then you can go like, I can delete those files. Then you back up and you delete the folder that has no files. And finally, at that level, or one level above the folder that you just deleted, one folder is gone. Then you have to apply the same thing to the other folders of that same folder. Go ahead, Izzy.
Can you like -R the folder?
Yep. The -R, guess what that R stands for?
Yeah.
Recursive.
Yeah.
Yep.
I mean, no one would do it manually.
Well, I mean, but that's basically what the program is doing for you, is to recursively delete files and folders. Hmm?
It's doing that when you right-click on it in Windows.
Yes. Yep. But the approach, but that's the approach. That's how we can get folders deleted. Did you want to? Yeah. Mm-hmm.
So you said in computer science they create folders with recursion and trees.
Mm-hmm.
But can't you do that with a loop?
Yes. So as it turns out, recursion and loops are equally expressive, which basically means any algorithm you can express using recursion, you can use loops to express those algorithms, and vice versa. Any algorithm that makes use of loops only, you can also express those using recursion. So they have the same expressiveness, but sometimes one is handier, the other one is just more painful to use. Okay, go ahead. Back there and then back to you.
Is there a reason as to why computers delete it like that? Like, you have to go deep into the folder to delete a file and then remove it, as opposed to like just nuking the whole folder?
The idea is you have to remove all the files first before you remove a folder, because what a folder technically is a catalog of the files that are under it. So that means if you can delete a folder without first deleting the files, those files will still be quote-unquote existing in the file system, which means those sectors, those resources cannot be reclaimed anymore. And yet you have just lost the last catalog to those files, but those files are still somewhere in the file system. So you have just lost storage, if you did that. Okay? Yep, go ahead.
The power behind using a subroutine versus actually using loops is that we can define a subroutine once and invoke it multiple times, whereas opposed to with a loop, we would probably have to code every single loop.
Something like that, okay? But in more complicated recursive subroutines, then the issue is you're breaking up a problem into one, possibly more subproblems. But each of the subproblem looks just like the original problem. So you can call the same subroutine to solve those subproblems, except you're passing on a smaller problem onto the recursive call. So when you have multiple subproblems, then the power of recursion over loops is really going to shine. I can give you one example as a maze, okay? So you imagine you're in a maze. where you can get into a particular cell and there are like multiple openings. And your objective is to search the entire maze for something. You're just collecting precious stuff in the entire maze, so you want to traverse every single reachable path. Okay? So what do? You look at all the 3 openings, right, front, and left. Okay? And you go like, well, what do I do? Well, I'm going to do it in this particular order. Okay? I'm going to explore using the order of right, front, and left. Okay, so you turn right, okay, and you go into this corridor, and at some point you see the same situation. You have 3 ways of proceeding. What do? You apply the same thing. So you basically keep doing this until you hit a dead end. So when you hit a dead end, you back up until you get to a junction where you have alternatives again. But recursion means, it keeps track of which branch you have already looked into. So now you can say, oh, I looked into the right branch already. Now we can just go for the straightforward, the ahead branch. So that is one use of recursion that makes the recursive solution a lot simpler compared to the iterative or loop-based solution.
So a loop wouldn't keep track of where you've been.
A loop, not without extra work, extra variables, and basically we have to use an array as quote-unquote a stack. Now, we haven't really talked about a stack in this class, so I'm not going to get into it, but you have to utilize extra constructs in order for a loop to handle that type of situation. But it can, it's just not very intuitive. All right? Okay, so I put up this page because I want to illustrate how expressions on a daily basis can be seen as a tree. Okay? So we'll go dig up a kind of complicated expression of some kind. Okay. Or I can just kind of make up one too. Okay, we want to look at images. No, these are way too simple. I like this one. Let's try that one, okay? So we'll try this one, and I'm going to copy this onto the tablet first, and then we'll talk about how it can be seen as a tree. So it's sine of y minus the cosine of y, the whole thing divided by 1 plus y squared, and then we take the square cubed of the whole thing, and then minus 5. Okay. All right. So this entire thing can be seen as a tree. So when we see this as a tree, we are asking, what is the last operation of the entire expression? It's got to be the minus, right? The subtraction. So we say there's a subtraction here. There are 2 things we need in order to perform a subtraction. One side is really simple. It's just a 5. The other side, the last thing, is to the power of 3. Okay? So, oops, I used the wrong representation here. So the other side is taking the power of something. Okay? So we say power. This is 5. So we have to, when we take a power of something, you have to specify to the power of what, and you have to specify the base. What is to the power of 3 in this case? So the last operation of the stuff inside the parentheses is the division. So we say, something divided by something. And then you have to specify the numerator and the denominator. The top part is the result of a subtraction. The bottom part is the result of an addition. What are we adding? We are adding 1 to power to the power, something to the power of 2. So here's 2, and here is y. Okay? Now the other side looks, it's not really that much more complicated. So we look at this as sine of something, cosine of something. Fortunately, in this case, sine only takes one thing, so it just has y in it, and cosine only takes one thing, which is y in it. So that's kind of how we look at an expression as a tree. Okay? So how do we have a computer to evaluate this expression and give us the actual value, given you have a particular value of y? It traverses this tree to figure it out. Traversal simply means a way to get around something. So when you traverse this tree in a particular order and perform the calculations, then you can get the result back. We do it also too. I mean, as humans, we do it the same way. We traverse quote unquote a tree. We are just not aware of the data structure behind the whole thing, and we just don't call that a tree. But it's the same idea. Okay? All right. So I need some time for myself to calm down and stop the obsession of going into trees and stuff like that. So we'll take a very short break, okay, 5 minutes, and when we come back, we'll take a look at some other recursive stuff, maybe go into parameters and local variables. So right now is 51, so we come back at 6:56. And I'm going to drink some coffee to heighten the symptom. Yeah?
We're able to show you, or after you're done, can I show you my accent on how I want to show you later?
Okay, sure. All right. You-
Take weights class.
So let me double check the recorder. The recorder is still on, it is still streaming. And so we can now continue. All right. All right. So we are going to continue with just maybe one more example on recursion. It's called the Fibonacci number or the Fibonacci series. So Fibonacci, there we go. There are two ways to define the Fibonacci sequence. One is recursive. So if you look into, there we go. So f of n is f of n minus 1 plus f of n minus 2. So that's a recursive definition. Now, is that the best way to calculate Fibonacci series? No, not even close, but it can be defined that way. Okay, so it's basically looking at a problem as subproblems, but each subproblem has the same nature as the original problem. So that's the whole concept of recursion and why it is useful. All right, so we're going to close this and then continue with our topics. So we go back to modules. So we are basically done with the first module under subroutines, invoking and returning. So we are now going to get started with local variables and parameters. Open it in a new link. So I did not actually rewrite the whole thing. I just reran the script to regenerate the document. So it was regenerated a little bit earlier, but it's not in the format that I want to use. So the concept of a local variable is the subroutines can keep track of their own variables, which is separate from the other variables that are not inside a subroutine. That's the kind of the concept.
So you can't use it outside the subroutine.
It is not visible from outside of the subroutine, and you cannot access it from outside of a subroutine. And they may not even exist outside of a subroutine either. So let's go ahead and take a look at some examples. So here we have an example with two subroutines, and we can see how the sub2 is being called from outside of any other subroutine. And sub2 is here, it is going to invoke sub1, okay? And both of them want to use I as a variable to control the looping. So in this case, we can see how there's a loop in sub2, making use of I to go through 2 iterations of this thing. And then we have another loop inside sub1 to go through 2 iterations inside the other subroutine. So, and in this case, I use this particular notation of local I to designate I as what we call a local variable, okay? And we use I to designate this as a local variable. So the way we want to explain this is to say, okay, what if we don't have local variables? What if imagine line 2 and line 11 are not here? So we have one single variable I, just like x in the previous example. What is going to happen in this particular code? Well, it becomes an infinite loop. Actually, I take it back. It doesn't become an infinite loop. It becomes it would do it once, okay? It would do sub1 once, and then it's done, okay? All right. But before we go do that, let's think about sub1 itself and just say, okay, within sub1, just analyzing from line 1 to line 8, what does sub1 do? What is the observable output of sub1? It prints x how many times? Twice. Okay. All right, so not very difficult to analyze. Huh? Because I is a variable to control the iterations, it is initialized to 0, and the loop says as long as I is less than 2, we have to keep performing the repetitions. And each repetition is only going to increase I by 1. So how many times do you have to increase I by 1, starting from 0 until it gets to 2? Twice, right? Okay. But every time you increment I, we are also printing x once. So how many times do you think it's going to print x? 2 times, right? So that's why. Okay, so that's how we analyze that loop. But applying the same analysis, we can look at sub2 and go like, oh, okay, sub2 is going to call or invoke sub1 twice. And each time we invoke sub1, it prints x twice. So that means the way this is supposed to work, we should print x 4 times, right? Because each time we invoke sub1, it prints 2 x's. And since we are invoking sub1 twice from sub2, that means we're going to end up with 4 x's printed. Okay? But if we do not use local variables, we can see how that is not going to happen. Go ahead.
Okay, because I was just going to ask, like, so the localized one, because if it's going to print the x twice, then why do we have local I in there?
So let's imagine there's no local I and see the effect, okay? But does everybody understand the intent of this code? In sub2, I just want to call sub1 twice. In sub1, I just want to print x twice. And they're supposed to be independent from each other than one is being invoked by the other one. Okay? So the first thing we'll do is we'll imagine that line 2 is not here. We are not designating I as a local variable. And we'll imagine that line 11 is not there either. So we do not use any local variables at all. We just use the same variable concept that we have been using all along. And then we'll see what happens, okay? So let me put this into the spreadsheet first, okay? And I can just type the whole thing. So we have define sub1. I get 0, so we don't have a local variable I this time. I is shared between the 2 subroutines now. So while I is less than 2, do print x. I gets I plus 1, and while, and define sub 2. I gets 0 again, while I is less than 2, do. Yep. Mm-hmm. On which line?
So line 8 and line 1, we have define sub1. Sub1 is just the name of it. Is there a reason why we don't like?
No particular reason. Typically, in a real programming language, you do not use parentheses around the name of the subroutine, but you do put parentheses around a list of parameters. So we haven't really gone to that part yet. So we invoke sub1. I gets I plus 1. And while, and define sub. I'm just retyping the program, but without the local. So we invoke sub2 here, and then we'll go ahead and fix the indentation. And then down here too. All right. And give them, I'm not going to give them line numbers because I can use the row number as the line number. So I'm going to delete column A. So this way we're just using the code and the row number as line number. And then we'll trace it on the other side. And let me go back to this one to show the algorithm. And then the other one to show the trace. There we go. And we want this to be just a little bit taller, like that. Okay. Oops. There. Okay, so now we can start to trace it. With this one, we'll need line number. We can't really see all the line numbers because I moved it a little bit too much. There we go. Okay, so we got line number, we got comments, because we do have a loop, 2 loops. And then we have one single variable I. I is not a local variable, so it starts to exist from the beginning of the execution of the program. Yes?
I just have a question. This
Yeah.
is not a recursion, right?
This is not recursion. We are basically done with the concept of recursion, at least for now. Okay. So here's the precondition. I doesn't need to start with any particular value because it will get destroyed or overwritten before we start to use it. Not right away, but eventually. So we start execution on line 15, which is the first line that is outside of the definition of a subroutine. And that's going to make us allocate a return line number column. And then we remember, when we come back, it is already done. So go to post when we are done. And then we go to the first line inside sub2, which is on line 9, which initializes I to 0. And then we get to line 10, which asks the question, is I less than 2? Well, it is true. Then we go to line 11, which invokes the subroutine sub1. So we allocate, once again, the leftmost available column, which is column E this time. We label it as return line number. And then we say, what is the line after invoke sub1? It's line 12. Okay, so we go to line 12 here. And then we continue execution at the beginning of sub1, which is on line 2. And we reinitialize I to 0. So this should be a clue that something is not right, because we're using the same variable for counting. It is the same variable, because we are not using local. Okay? This is without any locals. In other words, I am using the code exactly the way it is on the left-hand side right now, without any local definition. So there's only one single variable called I, and it is shared by both subroutines. If one subroutine changes I, it is the same thing that will eventually be used by the other one. Yep?
How do we differentiate local variables in a trace?
So when we trace the other one, we'll see. Okay, that's a good question, but we'll see it when we get to that part. So now we're on line 2, moving on to line 3, which also has the same question. Is I less than 2? It is true. Then we go to line 4. We print X. So there's really no output of this entire program. So when you print something, we'll just say, okay, X is printed to an imaginary screen. And then we get to line 5, which adds 1 to I, but it is the same I, okay? So this I is now incremented to 1. Then we go back to line 3. I is less than 2 is true. Go back to line 4, print X again. Then we go on to line 5. I is now 2. Then we go back to line 3, and I is less than 2 is now false. Is that okay? Did we get out of the loop? There's nothing to do after the end while, so we get straight to line 7. So now it's time to return from subroutine sub1. When we return, we locate the rightmost return line number column, which is column E this time, and it tells us to go back to line 12. So we write down that we're supposed to go back to line 12, and then we just say, okay, that column is no longer in use, so we use strike through to mark that column is now not used anymore. So now we continue execution on line 12. What does line 12 do? Add 1 to I. Which I are we talking about? There's only one I. All right. Now it gets incremented to 3. And then we go back to line 10. And of course, the condition of line 10 is going to be false now. And then we go to line 14, which locates column D as the return line number. It tells us to continue execution at post. Then we deallocate column D, and we're done. Oh, but it only printed X twice instead of 4 times. What happened? When we increased I to get out of the loop in sub1, that is the same variable I that sub2 was using to count how many times it's supposed to go through its own iteration. So by the time we return from sub1 to sub2, the variable I is already 2, which is already greater than 2, greater than or equal to 2, and that's why this doesn't work. So in order for this to work, there are a few ways to do it, okay? We can use different variables, which makes perfect sense, right? So we can change this code so that subroutine 1 uses variable I, and then sub 2 uses variable j. That will solve the problem. Yep.
The problem is when you run into like a big program, you're going to have more
Yep.
variables and they might have overlapping needs. If they're
Exactly. And nobody can tell you, the compiler will not tell you that your variables are being shared. That is the biggest problem. How many subroutines do you think is present in a particular program? We're talking about a sizable, actual, useful program. How many subroutines are we talking about? Just the order of magnitude. Hundreds to thousands, okay? In other words, you'll be running out of all the letters in the alphabet, just like that, okay? And all the common variable names will be gone first, okay? Counter, gone. Sum, gone, okay? And the worst part is you don't know whether you have accidentally used a variable that somebody else is already using. Another subroutine have been using this already. The compiler won't tell you, okay? Because variables like I in this case, they're called global variables. And by intention, they are supposed to be shared by subroutines. So the compiler obviously is not going to tell you, hey, this subroutine is using that variable that is already being used by that other subroutine, because the compiler cannot tell the intent of the variables. It can only say that, well, it's a global variable, it's supposed to be shared, so I'm not going to tell you that these two subroutines are using the same variable. Well, there are other ways to fix this problem. We can always prefix the name of a subroutine, the name of a variable with the name of the subroutine. So this way it becomes sub1 underscore I, sub2 underscore I, and so on.
you'd run into problems though if you had like auto-completion while writing code, or if you weren't keeping track of what variable you were trying to call. Like
Well, if you have a typo,
yeah.
then you'll be stepping on somebody else's variable without even knowing it. Okay, so once again, it goes back to the problem of the compiler is not going to help you. Okay, that is your rule, it is your rule of thumb, but it is not something that's enforceable by the compiler. Okay, so that approach doesn't work. Now, there's one other problem, which is kind of like a minor issue, but it's worth noting, is if every single subroutine has its own variables that are quote-unquote independent to the rest, then you have a lot of columns used, even though only one is being called or one is being used at any particular time. Is that okay? So let's say you have 500 subroutines, and each subroutine has, okay, let's just say 3 variables that it needs to use. So now you have 1,500 variables altogether. Then you have 1,500 columns, okay, basically allocated from the beginning of the execution of the entire program, even though at any particular time, the call tree or how deep the invoke can get, maybe only up to 6 or 7 is kind of extreme already. So only 6 or 7 subroutines are actually being invoked at any particular time, but it's using the space of 500 subroutines. That doesn't seem to make sense, okay? That doesn't seem to be very helpful. And then the last reason, there are 2 last reasons why global variables are not really helpful or useful in situations like this. One has to do with recursion. Okay, if you only use global variables, recursion does not work very well. Okay, and then the second reason is reentrancy, which is a term that you probably will not see until an upper division class in a computer science program. But reentrancy is one of the issues with global variables, and the use of local variables would solve all of those problems. Is that okay? So now we'll go through the same program, but this time we'll put local I back in, and we'll find out what is the difference between a global variable, which is what we see here, versus a local variable, which syntactically speaking is really, really similar, but when we actually run the program, it is very different. Okay? So are we ready to kind of introduce local variables? To introduce local variables. Yep. So this is global. Okay. This I is global, and we're going to introduce a local, the concept of local variable now. So to do that, I'm just going to do some copying and pasting. So the algorithm looks almost exactly the same, except that before line 2, I just have one little syntax thing that says, oh, this is local I. It is more like a destination than something that actually that we have to do. It is really just saying, yeah, there's a variable called I, but it is a local variable this time. And then we'll do the same thing over here. Right before line 10, we'll insert a row that says exactly the same thing. I is a local variable. So in terms of the syntax or the code of the program, we're only introducing 2 lines. Okay, it doesn't seem to be a whole lot. But when we trace this algorithm, it becomes very different from the last one. So we'll go ahead and trace this algorithm. And we start with, in this case, the first line that we want to, so okay, let's make all the columns first. We have line number. Every single trace has line number. We have comments because we have loops. Okay, so every program that has, every algorithm that has conditional statements or loops is going to have the comments column. And that's it. We don't have a single column for I at this point. So, so what do we have to say about the precondition? Absolutely nothing. There are no variables to say anything about as a precondition. That's kind of weird. So if there's no column for I in sub 2 and there's no column for I in sub 1, how does this program work? Well, for the time being, we'll just say that they're not here yet. They do not yet exist. So now we get to line 17. Okay, after line 16, we go to line 17. So line 16, oops, excuse me, line 17. The first line outside of the definition of any subroutine is line 17, so we start with line 17. Line 17 says invoke sub 2. Don't we know how to do invoke by now? Okay, so we allocate the leftmost available column, we label it as return line number, and then we write down where the subroutine is supposed to go back to, which in this case is post. And then we get to the beginning of the subroutine, which is on line 11. Local I doesn't do anything. It's a declaration, but it doesn't really do anything. But wait, there's one more thing we need to do now. Because I is a local variable, it starts to exist when the subroutine containing it is invoked. Okay, let me say that one more time. Because variable I on line 11, excuse me, line 10, is a local variable, it does not exist until the subroutine is invoked. Okay? Okay, now that it exists, where do we put it? Where do you think we should put it? Hmm?
So it was invoked on line 17.
It's invoked on line 17, and it has to start to exist, and it exists now. So the moment you invoke a subroutine, the local variables of that subroutine will start to exist. Okay? So now we have local variable I using column D, and it starts with an unknown value. So we put a question mark there. This is the biggest difference between a local variable, which starts to exist as soon as your program starts to run, as opposed to a local variable which does not exist until the containing subroutine is invoked. Is that concept okay? All right. So you're asking me to do something that's really hard for me to do, because when I say something, I don't remember what I just said. So I can approximate, okay? I can try my best. A local variable does not exist until the containing subroutine, which in this case is sub 1, is sub 2 is invoked. So the invocation itself creates the local variable. So when you create return line number, that's also when you create the local variables. Yep.
Okay, I have a question.
Yep.
On sub 2,
On sub 2,
say you have another local variable
uh-huh.
that was on line 14.
On line
Instead of
14.
There's another local variable
Uh-huh.
you declare it.
All the local variables start to exist. Yep. Well, for the purpose of this class, we'll make that assumption. In C and C++, it gets a little bit more complicated, but the concept is the same. Okay. So we just basically, in this class, we say that when you invoke a subroutine, every single local variable that it declares start to exist at the point of invocation. And they all use up columns, additional columns that we allocate, just like return line number. Okay? So the next line is line 11. Line 11 refers to variable I, but which I are we talking about? Well, there's only one at this point, so it has to be referring to column D. So column D is now getting a value of 0. Then we get on to line 12. Line 12 is evaluating is I less than 2, and the answer is true. Then we get on to line 13. This is where the fun stuff begins. Because line 13 is an invocation, so we do the usual boring stuff of, okay, we'll allocate the leftmost available column, we call it return line number, and then we indicate where to get back to. The invocation is on line 13, line 14 has something to do, so we say the return line number is line 14. Nothing exciting at this point. Oh, but wait, sub1 has a local variable too. It is also called I. That's fine, not a problem. So now column F is now allocated, and it has an unknown value to begin with. So right now at this point, the program actually has two variables. They're both called I, okay? But one belongs to subroutine sub2, the other one belongs to subroutine sub1, okay? Now, after setting up, the columns, we can now get into the subroutine sub1, starting from the beginning, which is line 3. So line 3 immediately has a problem because which I am I talking about? Are we talking about column D or are we talking about column F? Column F, okay? It is always the most recent definition or the most recent declaration that you have encountered. So when you look up a variable of a particular name, you're always looking up the rightmost column with that name. So even though we have two columns, with the label I, column D and column F is the rightmost one, and that is the one that we're going to use. Is that okay? Yep.
Are there any other ways that you can make sure that you know this?
There's really no need to tell the difference between the two, because when you're in a subroutine, you can only refer to things that are either local to the subroutine or things that are global. So it doesn't matter what the other subroutines have, you actually do not have visibility to those variables. Yep?
Can a subroutine 1 invoke subroutine 2?
Yes, but then it will be recursive, because recursion doesn't have to be direct, which means, okay, subroutine 1 is invoking itself, that's obvious recursion. But if subroutine 1 invokes subroutine 2, and then subroutine 2 in return invokes subroutine 1, that is also a form of recursion. Yep. All right, so now we're on line 3. Line 3 says, I gets a 0, but it is the rightmost definition or the rightmost column of the label I. So now we are updating column F. And then line 4 is the same thing. When it refers to I, it is referring to column F, not column D. And now we go to line 5. Line 5 is doing the same thing, print X. We move on to line 6. We are adding one to I, so we are adding one to column F. You can see how this update doesn't do a single thing to column D. So the counter that we used in sub 2 is not touched, okay? Nobody can actually touch it because sub 1 cannot even see the local variable I of sub 2. So there's no way for it to touch it. All right, so after line 6, we go back to line 4. So this loop is kind of doing the same boring stuff as before, except it's using column F as a counter. Oh, this is printing, which is just here. And then line 6 is updating column F from 1 to 2. And then we get back to line 4. I is less than 2 is finally false. And then we exit the loop. We get to end define sub on line 8. We do the same usual boring stuff when we return. Okay, we look up the rightmost return line number column. It tells us to go back to line 14. Okay, so now we just make a note that we need to continue on line 14. And then we say, okay, this column is not of use anymore. Let's deallocate it. Okay, so we go to here. We just, this is really just how I denote a column is not used anymore. But now we have a problem because, oh, column E is gone. It is deallocated. What about column F? We have to do the same thing. So a local variable does not exist until the containing subroutine is invoked, but it gets destroyed or deallocated when the invocation is done. Okay, so we do the same thing with I. Okay, we say this column is no longer useful, and then we use strike through to denote that. Is that okay? So now we're back to line 14. Line 14 is just adding 1 to I. Which I are we talking about? Column D. Yep, column D sets. Okay, we go from 0 to 1, and then we go back to the beginning of this loop on line 12. I is less than 2 is true. Yep.
For line 13, after we go allocate, can we basically copy line 7 through line 8, or excuse me, 18 or 17?
Even those rows. Yep. 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 We can just copy and paste it. So on line 13, we'll just go do exactly the same thing. In other words, this time we can just copy and paste this entire thing, because the entire subroutine call only affects the local variable, which gets reallocated along with return line number. They're both reallocated. We go through exactly the same code again, and then when we return on line 8, this time we return to line 14 again. And then I, which is column D, gets updated to 2. Then we go back to line 12. The condition is false this time. So we get out of the loop. We get to line 16. Line 16 looks up the rightmost return line number, which is now column C. And if you remember, column C has post in it. So we basically write down post first. And then we look at everything that were allocated for this invocation, the return line number, and also the local variable. In other words, now that we are at the end of sub 2, we take everything that we allocated for the invocation, both the return line number and the local variable, and then we say both of those are no longer in use anymore, so we deallocate both of them. Then we continue execution at post, which means, okay, we're done. There's nothing else to do. So are we doing okay so far with the concept of local variables?
Yes.
Okay, very good. I like that confirmation. Yep.
Except in D, is it strike through 1 or strike through 2?
What again?
In column D on line 16?
On line 16, it is striking out the I. Yep. So this is a pretty new concept. It is a combination of variables and invocations. Okay, I meant to actually go back to the previous one to illustrate one point. So let me go back to this thing here. If you look at column E, it is representing one invocation of the subroutine. F is another invocation. G is another invocation. H is another invocation. So that means at this particular point in time, there are 4 invocations, one on top of another, of the same subroutine. So there's one subroutine. I think I call that, how did I call that subroutine? Okay, this is sheet 6. So we look at 5, sub 1. Okay, so in this case, there's only one definition of sub 1. But at this point in time, there are 4 invocations of the same subroutine stacked up. Is that okay? So that's a kind of useful concept. It's not easy to understand, because we look at the static definition, which is in the pseudocode, but the runtime behavior, which is in the trace, is what we actually are using in terms of the computer's memory. So each invocation takes up resources. So the more invocations, the more resources it's going to take, even though there's only one single subroutine in this particular program. Is that concept okay? All right. Okay, so now that we have talked about this, let's go take a look at a recursive algorithm that makes use of local variables. Okay, so we'll go take a look at one, and we'll say define sub. We'll call it fact, okay, for factorial. And then we'll use a global variable for a particular use. So, okay, we'll use local n, okay, and then we'll say n gets x if n is greater than 1, okay. Then we do the recursion, and the way we do the recursion is x gets x minus 1, and then we invoke the subroutine called factorial again. And when factorial comes back, we have to say r, which stands for result, is r times n. And we have an else here. So the else is the result gets whatever x is, no, or n. And if, and define sub, and then initially we'll set x to, just thinking about how much do we want to go through this. 2 would be fine. Well, 3 is better. There we go. Invoke fact. There we go. So this is the new subroutine that we're going to trace. It does make use of the concept of a local variable because n is a local variable. And it also has the same kind of elements that we have been talking already, which are basically variables, assignment statements, conditional statements, that sort of thing. There we go. All right, so this is the pseudocode, and here we're going to trace it. Okay, so we got line number, we got comments. So now we want to look at, okay, so how many variables are global this time, and how many, there's only one local variable, but there are 3 names referred to, so that means the other 2 are global variables. So can someone tell me which 2 variables are global? Go ahead. X and R, okay, so we got x as a global variable, r as a global variable. So if a variable is global, it gets allocated when we talk about the line number, the comments, and stuff like that. They basically start to exist as soon as the algorithm starts, and they don't cease to exist until the very end. So they are always around. So now, in terms of precondition, we got something to say now, okay? We can say, variable x can start with an unknown value, and variable r can also start with an unknown value. Okay, so we want to use less space because we got stuff that we need on the other side. All right, so line 12 is the first line outside of the subroutine, so that means x gets a value of 3, and then we get into the invocation on line 13. So we do the same thing. We allocate the leftmost column for return line number, and then we remember when we come back, it is done. We write a post here. But we also have to allocate the local variable n for the subroutine fact, okay, which stands for factorial. All local variables start with an unknown value, okay? So you have to remember to indicate that when you turn in your trace. Yep?
So you declare the local variable when you invoke or call the function.
When you so when you invoke, so when you invoke a subroutine, then the local variables start to exist. So that's why you have to allocate while you are invoking the subroutine. Okay. So now on line 3, the first thing we do is we copy the value of x, which is 3, to the local variable n. So n gets a value of 3. And then on line 4, we evaluate the condition. N is greater than 1 is true. We go to line 5. Line 5 decreases x by 1. X is a global variable. So we go back to column C and decrease the value of x from 3 to 2. Then we go to line 6, which is the invocation. Same thing, we have return line number allocated, we have local variable n allocated. Return line number has to go back to line 7 because the invocation is on line 6, so the return line number is 7. N as a local variable always start with an unknown value. So now we have column G and column H allocated for the second invocation of fact. After we allocate those two columns, we continue execution at the beginning of the invoked subroutine, which is on line 3. And once again, we copy the value of x, which is now 2, to this variable n. And then we go to line 4 again. N is greater than 1 is true. That means we go to the then branch on line 5. We decrease x by 1. So it goes from 2 to 1. Then we go to line 6. We perform another invocation. So we allocate return line number as well as n. The return line number is 7 again because the invocation is on line 6 and there is stuff to do on line 7. N is now unknown because it is just allocated. So when you allocate for local variables, they always start with unknown values. And this is a very important point to remember, because if you don't remember that part and you start to read the value of a local variable, you have no idea what that value is going to be. And then we go to the beginning again on line 3. We copy n, x to n. So the last n here is now going to have a value of 1. We go to line 4. We evaluate the condition. N is greater than 1 is finally false. So we have to go to the else branch, which is on line 9. We copy the value of n to r. So r starts to have a value at this point. So r is just copying n, which is 1. And then we are done with the conditional statement. We get to line 11. So with n defined sub, which is the end of a subroutine, we have to do two things. We have to look at these two columns, but we have to make use of one. Okay, we have to say we're supposed to return to line 7, so we put a 7 here. And then we look at these two columns and say both of them are no longer of use to me, so I'm going to deallocate both of these columns. All right. Now we continue execution on line 7. Line 7 says, well, pick up n and multiply it to r, and then we store the result back into r. Which n do you think we are referring to? Which column? Column H. Because column H is the rightmost column that has the name of H. Okay? So we are now picking up this 2, multiply it to r, which has a value of 1. 2 times 1 is just 2, and then we store that into r, which is here. After line 7, we are done with the conditional statement. We get to the end of the subroutine on line 11. We do the same thing. We look up the return line number. Where we're supposed to go back to is line 7 again. And then we have no use of column G and H anymore. So I'll just kind of copy this over here because we are deallocating column G and H. Now we are back on line 7. But when we get back to line 7, we are not only are we getting back to that particular line, but the context has also changed. Because right now when it refers to n, it is referring to column F, not the other two n's, because those two have been deallocated already. So column F is now the rightmost column with the label of n. So we perform that calculation. N is 3, r is 2. 2 times 3 is 6. So we update variable r, which is a global variable, with a value of 6. And then we are done with the then branch. We get out of the conditional statement. We get to line 11. And then that's the end of a subroutine. We got two things to do. We look up the return line number. This time it's post. Good news. But we still have to remember to deallocate both of those columns. So we deallocate column E and F this time. Then we actually go to post, but post has nothing to do because it says, we're all done. So this is the trace of the factorial algorithm using only local variables, a single local variable and global variables. Do we have any questions about this particular program or this trace? No questions. Yep, go ahead.
What would happen if you use the R multiplied by N if you put it before the invoke?
Before the invoke. Okay, so you're talking about line 7 and line 6 exchanging the positions. Then this N, this R would be undefined. Because this R doesn't get a value until we get to line 9. And line 9 doesn't execute until at this point when x is 1. So if you exchange these two, then you will be using an unknown value and multiply it by n, which ends up with another unknown value because you cannot tell what is the product of an unknown value and a particular known value. Question? So in this class, I will not ask you guys to create or design recursive algorithms, but I do expect you guys to be able to trace it. So there's a difference between the two. Tracing it means you understand the mechanism, but to design algorithms using it means that you understand the concept enough to use it as a tool to design something. Question? Say when? If you do both, do we get extra credit? Well, I know. Exactly.
How about you give us a really hard one? To be extra.
There's no extra credit in this class, but then you get that nice and warm feeling that you'll be excelling in the next few classes, right?
So
Yep.
you'll have to design a recursive algorithm in algorithm implementation.
You don't really get to design recursive algorithms until maybe 430, which is data structure. That would be the first class when you actually have to write algorithms that are recursive. So we have 360 and 400 in between this class and 430. How many people know and how many people here are going after the computer science transfer degree? You're transferring to a 4-year. Okay. All right, so for those of you who are transferring, so 300 is here. It goes to 360. 360 is one of the most important classes because it can go in multiple directions. It can go to 310. It can also go to 400. 400 goes to 430. And then 430 is a co-requisite of 440. So 440 can be taken in the same semester that you take 430. But 440 also has a prerequisite of math 370, which is going away, but they have a replacement of that. 370 is pre-calculus. And if you're going after the computer science degree, you need Calc 1, 2, and 3 anyway, okay? So, so by the time you're taking 430, most likely than not, you would have taken the equivalence of 370 already. Some of you may be placed into Calc 1 to begin with, so you would have the prerequisite from the start. It's okay. Calculus is not my favorite subject either. I got 1 C when I was in undergraduate, and that was from Calc 2. I cannot even remember what Calc 2 was about. I just remember I didn't like the way the professor, taught the class and got a C. My only C.
C's get degrees.
Huh? So that's kind of the graph. So that means, by the time you get to 430, you would probably be required to write algorithms that are recursive to process, trees and other data structures. But before that time, you do have to understand what it means and how to follow the algorithms, but you probably do not need to write your own algorithm using recursion. Question?
Well,
310 is assembly language programming, which I teach every semester. Yeah, it's actually, technically speaking, it's computer organization and assembly language programming. So it has two components to it. One component explains what is inside the computer, the actual hardware, how it gets the job done. And then the second part is assembly language programming, which is the lowest level lowest level form of programming. Yeah, go ahead.
Oh, I just got confused because I'm in a 310 class, but it's CISC.
Yeah, C310 is entirely different from P310. Yep.
You take 310 and 400 in the same semester?
Yes, you can.
You said like you shouldn't know.
Okay, I will tell you that most people try to defer classes until the very last moment. Okay, so some people take 310, 430, and 400 in their very, very last semester. Some.
What do you mean? You take 310 and 400 and then 430 and 440 in your last semester?
You cannot take four. Okay, say that one more time.
So you would take 310 and 400 together in the same semester?
That would make more sense, yes.
And then you would do the last two.
Right, yeah. Yeah, taking 310, 430, and 440 in the same semester is doable. I mean, it doesn't mean it's not doable, but it does put a heavy load on that person. I teach, so 300 is not usually what I teach. I usually teach 310 and 440. Yeah, so I do have students, sometimes I have students in both classes, and sometimes they have both classes scheduled on the same final exam day, and it's brutal because most of the time they are adjacent, so both are evening classes or both are daytime classes, and they're next to each other, which means the final exam time is also going to be right next to each other. So they have like 4 hours of exams, and both from me. So yeah, so it tends to be a little bit brutal.
I've somehow managed to have you teach almost every single computer class I've ever taken, just by sheer coincidence over the years.
I would say that this is the second time you take a class from me because somebody else could not teach that class, and I'm it.
Yeah. It'd be like the fourth time I can remember having you.
Okay.
I don't know, my memory's terrible.
Okay, there was a question back there. Yep.
I was going to say, is 310 required?
For a computer science degree, yes. Yep. And we are in the process of converting our computer science degree to a computer science transfer degree. So that means, I cannot remember, the agreement between CSU, UCs, and the community colleges, we're slowly moving in that direction so that when you get when you get an AST, an Associate of Science Transfer degree, then you qualify to apply to a bunch of CSUs and UCs, but who accepts you depends on who else wants to go to those universities. So the universities can prioritize incoming students accordingly. All right. Any questions about the sequence of taking classes for the computer science degree? Of course, this is not taking into consideration the math, the physics, some of the other classes. Yeah. Question?
Which one do you recommend? C++ or Java?
Okay, so that kind of throws a wrench into the whole thing. So 360 can also go to 401, which is the Java class, and you can use the Java class to fulfill the requirement of 430. Okay, so if you take this path, it's okay. I think this is what Sac State wants, because Sac State wants Java. They don't want C++. Okay. As long as you take 360 before 310, you'll be fine in 310. Sometimes I get students from Sac State, and they have not taken C and C++, but they have taken Java, and they take CISP 310, and they will struggle, because there's a concept in C and C++ that is absent in Java. So somebody who only knows Java but not C and C++ won't be able to get 310 as quickly.
I'm going to take the 360, but my question is, because I'm not sure about Java or C++. Somebody tell me Java is better.
Quote unquote.
Some is, yeah.
Well, okay, so in this case, the pragmatic consideration, regardless of which language is actually better, is which school or which university do you want to apply, and which class articulates with that university.
C++ better, right?
C++ gets you to more universities. I think there are very few universities that would take Java as a language. So you have to look into assist.org and find out, which university accepts Java and which university accepts, C and C++. But I know that, once we convert to AST, the associate degree, Associate of Science transferable, it's going to be C and C++ only. Java does not meet that requirement. So that means at some point, Sac State will have to change too. So is that addressing your question? Okay, you're welcome. Any other questions about the sequencing of taking classes? Yep.
What did you say that
310
310 is about?
is, okay, so I can,
Basically, you're working with processors.
What concept did you say that in C++ that
You're programming
Pointers.
What pointers?
Pointers, yep.
So, general languages like C and C++, program
We have a
that
question.
creates a
Why are there
subprogram
pointers in
that
some
interacts
places
with the
but not in
processor.
others?
Say that one more time.
Why are there pointers in some languages but not in others?
Because in assembly, you have to understand the concept of an address versus the content at the address. And that's basically dereferencing in C and C++. I mean, obviously, I'm talking about concepts that are outside of the scope of this class, but I'm addressing your question, because in Java, there are no pointers. Java has no concept of a pointer, and as a result, when I use the analogy of pointers in CRSP 310, people with a background of Java would have a hard time understanding it. Just to give you a preview, okay, of what CISP 310 is. So this is the outline of CISP 310, which is also what I'm teaching. I'm teaching 2 sections of 310 this semester. So it talks about physical states, numbers, and computers, base conversion, talks about base 2, base 16, base 10, how we convert between the bases. It talks about how to add binary numbers. So at first, it will start with just arithmetic stuff, and then it would transition to logic gate stuff. It talks about binary number subtraction, signed value representation, because when you only have zeros and ones, how do you represent something that is negative? Okay. It talks about floating point number representation. When you have zeros and ones only, how do you represent the value of pi, for instance? Okay. And then we transition to memory devices. And then it transitions to talk about compiling C programs into assembly code, and also all kinds of other stuff. Okay, this is a topic that you have seen already, calling and returning from a subroutine. And guess what? You will see that one more time in CISP 310, and you will recognize elements that we talk about in this class, except it has a much more formal name when we get to CISP 310. Just hold on 1 second. Give me 1 more second. Do you recognize this? Local variables and parameters?
Yes.
That's exactly where we are at this point in this class. So in CISP 310, we'll revisit that, okay? And if you take this class from me and you remember what I teach in this class, when we get to that point in CISP 310, you go like, oh, I get it. I already know that stuff, okay? So there are reasons why I teach this class in the way that I teach this class, because it's the very same stuff that you will need in CISP 310. Yes, now I can address your question.
Are there any classes in the CISP where you create an interpreter?
Where I
Where you create an interpreter?
create an interpreter? No, we do not create any interpreter, but I do have a processor that I designed for this class so that concepts can be understood using that simulated processor. So it's not an interpreter per se. Yep, so there's a very strong correlation between CISP 310 and the way that I teach CISP 310. So there are reasons why I structure this class the way that I do, and there are reasons why I use a trace using a spreadsheet the way that we do in this class. Okay, any other questions? Am I going to? Oh yeah, we're going to use spreadsheets big time in Crisp 310. And you will recognize, and you will, okay, let me pull up one page, okay? Since somebody asked, right? Somebody asked and I have to answer. But I'm not sure where I put that spreadsheet. I might have actually deleted that already. But give me another 2 minutes to, well, maybe a minute to try to find it. Okay, so TSB, do we still have that? Yep, okay, good. Okay. Yeah, so this is a good one. Okay, change from standard to just text, import. Okay. Okay, so but do you see something that you have seen already in this class? A spreadsheet, okay. And if you look at all the zeros as blank, okay, do you see how we're using the columns? You know, we will use up all the columns on the left, and then we start to use the columns on the right. It's the same concept, except, you know, in this class, we have a very formal name. We call it a stack, okay? In this class, in 300, I just say, oh, it's a spreadsheet. You know, we use the leftmost available column, or we look up the rightmost column that is in use. But it's the same concept. So there's a strong correlation between this class and the way I teach it and assembly programming. Yep.
So what is the purpose of the stack, and what would you need?
Well, you will learn that in 2 semesters, about this time too. Or you can just watch my videos for Crisp 310. Yep.
Not all your courses are 8 weeks.
This class is usually, you know, taught as a 16-week class. I think they made a 8-week class because many people try to enroll in the 16, and then there's enough for one class to open as a second 8. So that's why we offer a second 8 version of this class. But with most cases, you know, with most of these classes on these lists, they're all 16-week full semester classes.
Okay, 'cause I have to take 360 next semester.
Yep.
I couldn't get a full semester.
360, most of these classes, including this one, is probably best if it's a full semester class, because, you know, there are a lot of concepts to go through, and 8-week class is very compressed. Yep. All right. Well, if there are no more questions, I will let your long weekend start 5 minutes early.